Welcome again, guys and girls, to chapter 5.4, the derivative of some trig functions, basic trig functions. So for this first lesson out of the textbook, sine y equals sine x and y equals cosx. Lots to talk about with trigonometry, and I know typically a lot of students have varying challenges with trigonometry, varying experiences with trigonometry. I really enjoy trigonometry, and I think it's a really valuable a skill and knowledge base for students, math students, to begin to show their work with trigonometry and really understanding functions. So we're not going to have the time to review a lot of the things you would have done in the past with trigonometry. In the past courses with calculus here, I've taken a day or two and reviewed some trigonometry, common principles of trigonometry, a quick review of some basic trigonometry identities and solving trig equations, for example, talking about the cast rule, doing all these types of things here. We will do these as we come upon them in the examples and the homework problems for this particular section. But we're going to jump right in and talk about these two derivatives here and do some applications of trig functions and derivatives using the chain rule. So a lot of this kind of work here. Okay, so right off the bat, the derivative of the sine function, it is the cosine function. That's something that you'll see time and time again here. Okay, the derivative of the sine function is the cosine function, and the derivative of the cosine function is negative sine. Okay, written as the prime symbol, I have it here. That was that's sine x prime is equal to cosx, and cosx prime is equal to negative sine x. Written in Leibniz notation, if the function is y equals sine x, then dy dx is cosx. And similarly, if y equals cosx, then dy dx is equal to negative sine x. Two very simple rules to follow. Two very simple rules to implement and get derivatives from. And following some application questions, it's not going to be a big deal. The problem is, again, like every one of these functions, the functions get pretty serious, and students tend to just break away from doing just basic common math, right? You freak out a little bit, you get a function, you're not 100% sure what the function looks like and all that's involved in it, and you go and make a silly mistake when you have to find the derivative. Okay, so I want to make sure we're clear on these two basic rules here right off the bat. Okay, and we'll use these a lot here in the next half hour. Okay, the proofs. So, well, sorry, first of all, we're going to talk about the composite function. So if I have sine of a function, the derivative of that is cos of the function multiplied by the derivative of the function. And similarly, cos of a function, when I want to take the derivative of the cosine of a function, I incorporate the chain rule, so it's the negative sine of the function multiplied by the derivative of the function itself. Okay. Proofs involve some limit. Every derivative proof involves a limit, and in this case it is no different. We use the addition of the addition function, our formula for sine. We expand it all out. Okay, we do some rearranging and some factoring. Okay, we apply some limit properties, and we incorporate a few limit again properties here, and break this into pieces and parts. Then we evaluate our limit as h approaches 0. You can approximate this. This is not in a common, both of these in fact aren't common limits that you'd see and notice. So I've used an Excel spreadsheet that I think I put online. If you want to take a look at that real good proof of that, you can download this Excel spreadsheet and see that as h approaches 0, the function sine of h over h actually approaches 1. And similarly, 1 minus cos h is what I'm left with, divided by h, and as h approaches 0, that limit approaches 0 as well. All this simplifies down to cos x, and that's exactly what the derivative the derivative is. So the proof, it's just not some rule for derivatives that I came up with. There is a accepted proof from first principles involving limits, and the textbook goes through that. I've got an Excel spreadsheet in my course that supports that as well too. Okay, let's do some. All right, here's our function y equals cosx. So the derivative of cos is negative sine x. That's all you need to do. Okay, this is a composite function. Okay, so the derivative of sine is cos of 3x, but then I want to make sure I multiply it by the derivative of 3x, and that's 3. The proper way to write that is with the coefficient of. Okay, this next one. Y equals negative 4 cos of x over 2. Well, x over 2 is kind of hiding. That's 1/2 x. So the derivative, okay, the negative 4, I don't do anything. It's a leading constant. Okay, the derivative of cos is negative sine. Okay, and that's negative sine 1/2 x. Okay, and then I can close my brackets and multiply it by 1/2 as well, because that multiplied by 1/2 is the derivative of this composite function here, or this composed function here. Okay, so let's clean this up and bring this together. So y prime, I can go negative 4 times 1/2 times a negative 1. So negative 4 times a negative is positive 4 times 1/2 is 2. And then I'm left with sine of 1 over 2x, if I like. Okay, so those are my 3 derivatives. Okay, let's do a couple more here and jump right in. All right, this time we have a product rule. Okay, we've got a product. We've got x to the power 3 and sine x. Okay, so that's 3x squared, and the derivative of sine is cos x. So my resulting derivative function is y prime, and I'm going to do the proper application of the product rule. So that's 3x squared sine x plus x to the power 3 cos x. I can factor out, and I should factor out an x squared. I'm left with 3 sine x plus x cos x, and that's the derivative. Oh, this one here, okay, this is going to be a little bit more challenging. It's going to be a quotient rule. So I'm going to have e to the x and sine x. The derivative of e to the x is e to the x, and the derivative of sine x is cos x. Okay, so the one thing we're going to realize quickly here, I'm just going to give myself some room, that because of the symmetrical nature of the trig functions and the derivatives, right? Derivative of sine is cos, and the derivative of cos is negative sine. When you do some serious functions, you notice that they just fluctuate back and forth between sine and cosine. Okay, so you notice that there's going to be a lot of simplifying here, and a lot of identities and principles of trig come into play here. Okay, so now how do I do the quotient rule? I go up product, right? So e to the x times sine x minus e to the x times cos x, and then that's all over sine squared x. This would factor to e to the x sine x minus cos x all over sine squared x, and that's as far as I can go. This next one's just a full composite rule here. Let me just erase what I did. Okay, so I've got the derivative. Okay, I only have one x. I don't have 2 functions. I do have composite function though, right? Sine x and then ln, the ln of sine x. So I take the derivative of ln. Again, the derivative of ln is 1 over my composite function, and then I take the derivative of sine x, and the derivative of sine x we know is cos x. Okay, so I multiply these two together. So cos x multiplied by 1 over sine x is cos x over sine x, and I think you guys might remember that cos x over sine x is cotan x. Okay, got it? You want to take a break and take a look at some of these homework questions, maybe go through the online course and some of these examples, and just sort of catch your breath, and we'll continue here in a second. Okay, we've got 2 more, g and h here. So e to the negative x multiplied by cos x. That is a product rule. So I've got 2 functions here. The derivative of e to the negative x is negative e to the negative x, and the derivative of cos is negative sine. So it's a product rule, so f prime is going to be negative e to the negative x multiplied by cos x plus e to the negative x multiplied by negative sine x. And this simplifies down to, I have a hard time with that x box, so I've got negative e to the negative x cos x, negative e to the negative x times sine x, and I can take a negative e to the negative x out. That leaves me with cos x plus sine x. Okay, next one here. Something you may know and need to know about trig functions raised to a power. This is actually cos x raised to the power of 4. Okay, that's the proper way to write that. With trig, they just embed the 4, the index of the exponent, in between the trig function and the variable itself. This is very different from this question. Okay, this question is not the same. This is this would be, I take x raised to the power of 4 and take the cos of it. Okay, so if you see this notation, cos, okay, 4, okay, cos raised to the power of 4x is the same as cos x raised to the power of 4. And that's very different from the question I just talked about. Right, so that looks like it's a simple little power rule, right? Okay, and a chain rule. So 4 cos x to the 3, and then I have to take the derivative of cos x, and I remember that to be negative sine x. So if I clean that up a little bit, I'm going to bring my negative sign out, my leading negative, and it goes with the 4, and then I can write, okay, just like that. Good, making some sense. Practice these and try these. They're not as hard as it might appear. We'll get going on this. I'm going to pause it though and go into Desmos, and just want to take a little Desmos break and show you something to do in Desmos with the trig functions. Okay, I want to show you graphing trig functions in Desmos. Okay, I can do that like this. It comes in radian mode. Okay, notice that one full cycle, okay, would go from 0 to just a little bit over 6, right? And a little bit over 6 is 2 pi, right? 2 pi is 6.28, right? That's 3.14 times 2, and that's just about here. If I want to change that setting, I can do that here. The way you do that in Desmos is you actually type in, you can type in like -2 and the word pi. Desmos picks it up really nicely, and I could go 4 pi here, and I may want to do a step, and let's go pi divided by 2 might be a nice step here. And as soon as I do that, I've changed my graph settings completely. I may want to change my graph settings like that to y equals cos x. Does the same thing. Okay, I can even use theta if I like. Okay, I need to change it as a function though. I can use my keyboard. Theta should come up as a preset. There it is. And I just have to go here. Desmos still doesn't like it until I change it, and it just picks it up nicely here. Okay, I can also do another one here. Okay, if you like to use theta. Okay, generally, that's how you do this in Desmos. Okay, this is going to come in handy as we work through the rest of this chapter here. So let's go back to the lesson here and get on to a couple more pretty serious trig functions. Okay, let's break this. All right, sine of x squared. Okay, this is a little different one here. There's one variable, x, and there's two functions. There's a quadratic function, x squared, and there's a trig function, sine. Okay, so I need to take the derivative of sine. First of all, the derivative of sine is cosine, and that's x squared. And then I take the derivative of x squared, which is 2x. And the way I write that is 2x cos x squared. I can do that just like that. All right. Next one, sine ex. Again, there's only one x, so there's really Okay, it's not a product rule, it's not a quotient rule. There's one instance of x, my variable, and I need to do the chain rule across this. So y prime at x. Okay, so the derivative of sine is cosine. So I take the cosine of my function, and then I multiply it by the function itself here, and the derivative of the function, and that's written as. Okay, these are crazy functions. I'm going to graph that one here. All right, what about this next one? Ooh, this is a bit challenging. If I change it, does it help though? If I go rather than 1 over ln x, if I went ln x, okay, to the -1 and wrote it like this. So I've got 3 functions here. Okay, I've got a sine function, I've got a ln x function, and I've got a reciprocal function that's -1. So I've got to do lots of work here to find the derivative. So f prime at x, I take the derivative of sine first. I find the derivative of sine. Well, the derivative of sine is cosine. Okay, that's easy enough. Now I take the derivative of what's next here. Okay, how about my exponent, my reciprocal exponent, because that would be the next one I do first. The inner function ln x is left last. The derivative of ln x is left last. So now I'm going to take the derivative of something to the -1, right? This function to the -1, and that's -1 times the ln x to the -2. Okay, and then I can take the derivative of ln x. That's just 1 over x. Okay, so I can just bring this all together. Whoa, and that's a bit of a mess here. So what have I got here? Okay, I can go -1, okay, over the cos of 1 over ln x, and then that's all over ln x squared multiplied by 1 over x. If I want that further, okay, that 1 over x could be put in here. Actually, this 1 over x, let me fix that up a little bit here. I should have did this. Okay. So the 1 over x. It's like that. Okay, even simplified further. So I have a negative cos 1 over ln x over x ln x squared. That's a tough one. Wow. I'm going to go and graph this middle one here just to see what this function looks like here. This one might be pretty interesting, and then graph the derivative as well too. So let me just set the Desmos for a second, and I want to graph the what was my function here? Whoa, that's crazy. Okay, and then the derivative, I'm going to call this g at x, and that's going to be my derivative function. I need miscellaneous. There's my derivative function, and I can just take y, okay, and it comes in like that. Maybe we're going to change that a little bit. Okay, and change that to this. There it is. Looks a little bit stranger. Carefully, let me just hide this from view. That is crazy. Absolutely crazy. But look at that. Wow. Okay, so those are strange functions, certainly ones we've never seen before and work with. And do we need to know much about them? Not really. Can we take the derivatives? Yeah, absolutely we can. So, all good. All right, let's continue with a couple more here. More derivatives. All right, hang tight here for a second and we'll get going on these. Okay, chain rule for this one, okay? Chain rule for this one. Okay, so the derivative of a cosine is negative sine. So I've got to take the negative sine of sine x, okay, and then multiply it by the derivative of sine x, which is cosx. Okay, so this resulting derivative is going to be so that's actually a silly function here. Okay, taking the sine of a another trig function, the sine of sine x. All right, this next one, I'm going to change this to cos. I just find it easier to handle it this way. So the derivative would be the derivative of cos is negative sine, okay, x to the negative 2, and then I want to multiply it by negative 2x to the negative 3. That would actually look like this. I'd have a negative and a negative is a positive, 2x to the power 3, okay, multiplied by sine over x squared. And that's my answer here. Okay, next one here, f at x. Okay, the derivative of cos is negative sine e to the x squared. The derivative of e to the x squared, okay, is e to the x squared, and then the derivative of x squared is 2x. So my resulting function is negative 2x e to the x squared multiplied by the sine of e to the x squared. All right, crazy. Let's keep going here. I'm just going to double check that one. That looks good. All right, let's do an equation of a tangent line question. Okay, we've got, so I'm going to find this equation of a tangent line. So we've got to take our derivative. Derivative of sine is cosine. Okay, and I want to find the slope, okay, which is y prime evaluated at pi over 4. Okay, and that would be the cos of pi over 4, okay, and the cos of pi over 4, okay, is 1 over root 2. Okay, so I've got to plug this into, so with this slope and my point here, okay, so I've got to plug this stuff into y equals mx plus b. Okay, so y equals mx plus b, y is 1 over root 2, my x is 1 over root 2, my x is pi over 4 plus b. Okay, so just do a little bit of quick math here. I've got pi 4 root 2, 1 root 2, I'm going to solve for b. Okay, that's a little bit awkward. You guys maybe are not used to seeing what would be b. So back into my equation, y equals mx plus b, and my b is going to be 1 over root 2. Okay. That's the equation of my tangent line here. This is a little bit, okay, I think I've seen different solutions just before we're done this one. Different solutions dealing with this here, and that's what was this expression here. We could simplify that as a common denominator here. My b could be, okay, I could go 4 over 4 root 2 minus pi over 4 root 2, and write that as 4 minus pi over 4 root 2. So this could replace this in here, and that's just writing that expression as a common denominator. Is this one worth taking a look at in Desmos? I think maybe. Okay, so I'm going to pause this and go into Desmos and graph these two lines and take a look at this. Okay, there is the original function, the point, and the tangent line, and all working just perfectly fine here with this one. Okay, good. Let's go on and do, I think, the last example, the second last example. Let's go back. Okay, inflection points. Okay, so I need second derivative here, and okay, on the interval, okay, 0 to pi here. So my first derivative is, okay, the derivative of cos. Okay, so this is, we've seen this before, cos x squared. So my first derivative, it would be 2 cos x, okay, to the power 1, and then the derivative of cos is negative sine. Okay, so that would be negative, okay, sine x cos x. I usually write the sine first. Okay, now I need the second derivative, okay, and that's a power rule. So I'm going to write, sorry, product rule. I'm going to write that into 2 product x here. Derivative of negative 2 sine is negative 2 cos. And the derivative of cos is negative sine. So you can see something here. I talked about this earlier. As I take the first and the second derivative of trig functions, they all sort of circle back to the next one here. So I've got negative 2 sine x times sine x plus negative 2 cos x times cos x. Okay, so that would be negative 2 sine squared x, take away 2 cos squared x. Okay, and this this can be factored out. I can factor out a negative 2 if I like, and have sine squared x plus cos squared x. Okay, so now I want to find the points of inflection. Okay, so I need to take my second derivative equal to 0. Okay, so that's this expression equal to 0. It's already factored, and I know negative 2 doesn't equal 0, so my only part of this resulting equation, the product equals 0, is when sine squared x plus cos squared x equals 0. Okay, so how do I find sine squared x plus cos squared x equals 0? I think I've done that. I think I've made a small mistake here. I've got a product here. Sorry, my mistake right here. This is something I've got to go back and fix here. This is negative 2 sine x times negative sine x. So it'll be a plus. Okay, that's going to make that a. I'm going to stop it right here. Factor out a 2. And I'm left with sine squared x minus cos squared x. So I have to change. My apologies. I should have looked at my solution a little bit better here. So that's going to change that, and that's going to change that, and here that's going to put a negative sign in here and a negative sign in here. Okay, and how do I solve for sine squared x minus cos squared x? And I can take the square root of both sides, and I'm looking for situations here, okay, where this solution is balanced here. Okay, well, I only have a couple of different types of situations I can do and solve this for. I'm going to backtrack. Before I take the square of both sides, I'm going to backtrack and go up to here, okay, and make a substitution for cos squared x. And the substitution for cos squared x gives 1 minus sine squared x. So now I can isolate and start to solve for x. Okay, and take the square root of both sides. So I've got, and when I have sine x equal negative, or sorry, 1 over the square root of 2, plus or minus the 1 over the square root of 2, I know x according to my cast rule. Okay, according to my cast rule here, x would fall in. Okay, or my variables would fall in to these two intervals. Okay, where x would be here, and then x would be here, and that to me looks like it's pi over 4 is the first one, okay, and then the next one is 3 pi over 4. Okay, and they fall in. Remember that domain. That's why I've restricted that. So the first one is when I've got all are positive, so that would be when, okay, that would be, okay, when that sine x equals positive 1 over root 2. Okay, and the next one when we sine was positive, and that's the other situation, okay, where I have a second point here. And again, you guys did some solving of trig equations, okay, in advanced functions, maybe a little bit in grade 11. Okay, where these are my two answers here. Okay, you'll be asked to do a couple of questions like that as well too. I might have one more to do, yeah, real quickly. Okay, and okay, this is a function, and then I have to find the differential equation value of this. So it looks like I need an acceleration function. I'm given a displacement function. I'm probably gonna have to take the second derivative of this and get it going here. So I'm gonna pause and let you guys start this and see, and we'll be good. Okay, I need e at t. That will be 5 times pi over 10. Okay, that's the derivative of this function. And then the derivative of sine is cosine. And it's cosine of my interior function here. Okay, now let's take the derivative again. A at t. Okay, remember, because this is a and this is the second derivative. Alright, so now I have to take the 5 and the pi over 10. Now I can take the derivative of this again. That's another pi over 10. And the derivative of cos is negative sine, or pi over 10t. Okay, so this cleans up to 5 pi squared over 100 negative sine pi over 10t. Alright, my differential equation is this one here. Okay, so my left-hand side is my more complicated side. That's going to be a t plus pi squared over 100 as a t. Alright, I'm going to make some substitutions now. My a at t function I just found to be negative 5 pi squared over 100 sine pi over 10t. And then we'll close that bracket. And then I've got a plus sign, and I've got a pi squared over 100. And then I've got my displacement function. My displacement function is 5 sine pi over 10t. Looks like I can combine these together. Plus 5 pi squared over 100 sine. Okay. One's negative, one's positive. That's 0, so that equals my right side. And my differential equation up here is proven to be true based on this function and this first and second derivatives of the function. Okay, that's it for the chapter. You guys can get started on the homework questions. There's a few of them here. The solutions are posted in the homework help page, and we're good to go. Well, next one up will be the last part of this chapter, and that's a derivative of y equals 10x. So have a good one. Enjoy.